In this video, we're going to consider deformations, and we'll consider deformations due to forces and deformations due to temperature changes. So basically what we have is, like, say, consider a displacement due to a force call it P, and the displacement will be the force times the length of the part divided by the area of the face of the part times the Young modulus. Again, P is going to be the applied force. L is going to be the length of the part. A is the area of the face perpendicular to the force. And so, for example, if you have maybe a rod like this, and there's a force applied, say a force here, and the area will be the area of this face, of that face right there. Could be like a circle or a rectangle, something like that, but it's going to be the area of that face that's perpendicular to the force. And E is Young's modulus. And that's usually going to be found in the back of the book, whatever text you might be using. So that gives you the displacement due to a force, an applied force, a normal force. Then we also can have displacements due to temperature change. And that equation is given once again by delta. Sometimes you'll put a T for a subscript to recognize that it's displacements due to temperature change. And that's going to be your linear coefficient of expansion times your change in temperature times the length of the part. Once again, and L is going to be the length of a part. And then delta T, of course, is just the temperature change. And so we're going to look at some problems that involve these kind of displacements. And we'll first look at this problem here. It asks us to find the reaction at D. And we're told that there's a 200,000 Newton force applied. And it's A36 steel. So if we look up in the textbook, the back of the book, we can find Young's modulus. And so for A36 steel, we find that Young's modulus is 200 times 10 to the 9th. So for A36 steel, E is 200 times 10 to the 9th power. And so when we deal with a problem like this, usually the best thing to do is to use, I think, what the books call superposition. We're going to see how far the bar would expand or how much it would deflect if there was no wall. And then see what force is required to push it back to the wall. And so, first of all, see how far the bar deflects. Due to force P. If there was no wall. And so let's do that. First of all, you'll notice the way the force is applied here, it's applied right here. So it's just going to affect the length that's behind it. There's no force applied here, at least not right now, at least not until it hits the wall. So the force is only going to, it's applied right here. So it's only going to affect this 600 millimeter length. So again, let's calculate the deflection due to the force. Let me put a subscript of force P. That's going to be, again, PL over AE. And so again, we know that that's 200,000 newtons. And the length of that section there to which the force applied is going to be 0.6 meters. And then the area of that face of this section, notice that this is 50 millimeters, so it's 0.05 meter diameter. And so the area is going to be 0.25 pi 0.05 squared. And times Young's modulus. So the area of that face is here, Young's modulus here, PL, and you put that all in your calculator, and you get 0.000306 meters. So that's how far this thing would deflect, or how much deformation there would be here if there was no wall. So what you sort of have here is you have the force applied. And then this thing is gonna go out here past the wall. Again, let's say, again, I'm assuming, you know, here the wall is not there, so it's allowed to expand all the way out here. And so we'll see how far past the wall it went. So there was a gap of 0.15 here, 0.15 millimeters. So that means that this length right here from the wall to its farthest point out here is going to be 0.00306 minus 0.00015. So it's 0.00156 meters past the wall. In other words, this is how much it would expand if there was no wall. So now to find the force that's applied by the wall, you have to ask yourself, what force is required to compress this back to the wall? In other words, what force is required to push bar back to the wall? That is what force is required to push bar back 0.0000156 meters. And so we'll calculate that. So what we basically want to do is we have a picture here. And we're assuming this thing is out here. Then we want to push it back to the wall. So we want to force here, call it F of D. We want to know what is that force going to be. So our force then is going to be pushing all the way through here. That means it has to compress this whole assembly. And this is 0.6 meters long, 0.6 meters long here. And so we'll apply our force, our FDL AE. We'll apply that to this section. So the total deformation is going to be FLDAE applied this section plus FDLAE applied to this section. And we want that total to be this 0.00156. And so let's plug some things in here. Once again, the length for this section is 0.6 meters. The area of this face over here, if you look back at the beginning here, it has a diameter of 50 millimeters or 0.05 meters. So the area of that face right there is going to be 0.25 pi 0.05 squared times 200 times 10 to the 9th plus FD 0.6 meters, 0.25 pi 0.05 squared 200 times 10 to the 9th. And that's equal to that 0.000156. Oh, excuse me, I made one mistake here. This second diameter here was not 0.05, but 0.025, because if you look up here, that was 25 millimeters. So this second diameter right here should be 0.025 squared. And then we'll put all this together and solve for FD. And we get 20,420 newtons. That's going to be the force that's on that wall. So once again, just to review how we did this, we saw how much it wanted to expand if there was no wall, and then found the force required to push it back to the wall. Now we'll do a problem that involves temperature change. And we have this problem here. This assembly fits securely between the supports as shown. The initial temperature is 70 degrees. Determine the stress when the temperature reaches 100 degrees. So the first thing we'll have to do is find the force, and it'll be similar to what we do when a load is applied. First of all, what we probably should do, we see that we have a temperature change, so we probably should look up the coefficients of thermal expansion of each material. And those would be like our alphas. And we have 2014 T6 aluminum. And according to the book I have, its coefficient of thermal expansion is going to be 12.8 times 10 to the minus 6. That's for the aluminum. I'll put an A for aluminum. And then for the bronze, thermal expansion of bronze is going to be 9.6 times 10 to the minus 6. And for the steel, the 304 stainless steel, it happens to be that's also 9.6 times 10 to the minus 6. So remember, for this, we're going to use the delta T is equal to alpha delta T L. So our deformation is equal to our alpha times the change in temperature times the length. And so first of all, just like we previously, see how far the assembly will expand if there's no wall. So we'll apply this delta T here to each of these parts and add them together. So delta T is going to be equal to 12.8 times 10 to the minus 6. That's going to be our alpha. And then the change in temperature, we're told the change in temperature, let's say it starts at 70 degrees and finishes at 110. So our delta T is going to be 110 minus 70 or 40 degrees. So that's going to be 40 degrees. Then the length of that part is going to be 4 feet. But we're going to want this in inches. So that's going to be, this would end up being times 12. That's going to be for the aluminum. Then for the bronze, our coefficient is 9.6 times 10 to the minus 6. Delta T again is 40. The length of that is 6 feet. And convert that to inches, multiply that by 12. Then for the stainless steel, coefficient 9.6 times 10 to the minus 6. Delta T is 40 degrees. And the length of that part is 3 feet. And convert that to inches. And when you calculate all that, you find that it would expand 0.066048 inches. And it had started out at the wall, so that's going to be past the wall. So like we've done in the past, it's going to be this far past the wall. So we want to know what force is required to push it back that amount, to compress this that amount. So once again, what we use, so what force required? what force required to compress it that amount? And so just like before, we'll use delta equals PL over AE. But we have, again, we have three parts, and again, the force is going to be like from here, so it's going to be the same throughout. So if we use that, it'll be, so we'll apply this to the aluminum. So that's going to be FD, and the aluminum is 4 feet long, and we want to convert that to inches. And then the area of the aluminum is 12 inches in diameter. So the area of that is going to be 0.25 pi times 12 squared. And then we're going to need the Young's modulus for aluminum. And I didn't write that down, but that's actually going to be 10.6 times 10 to the 6th. And so that's going to be the deflection in the aluminum. And then the deflection in the bronze going to be FD times 6 feet times 12. And then the face area face there is 0.25 pi times 8 squared. And the Young's modulus for the bronze is 15 times 10 to the 6th. Then for the stainless, it's going to be FD times the length, which is 3 feet times 12 times 0.25. Let's see, the diameter for the steel is 4 inches. And then the Young's modulus is 28 times 10 to the 6th. So again, we have this aluminum, bronze, and steel. We used, the appropriate Young's modulus in the denominator, use the areas in the denominator, then use the length. And now we're going to set that all equal to 0.066048 inches and solve for FD. And then we get that FD is 277,742 pounds is the force. Now, finally, they ask us for the stress in each part. And so what we're going to have to do is, so for the stress, and let's start with, say, the aluminum. The stress in the aluminum is going to be our force divided by the area. And again, for the aluminum, our diameter is 12 inches. So the area is going to be 0.25 pi times 12 squared. And that's going to give us, calculate that. Looks like that is going to give us 2455 pounds per inch squared. Then the stress in the bronze, same thing, it's going to be the force divided by the area of that face, and that's going to be, let's see, for the bronze, it's a 8-inch diameter. So that's going to be 8 squared. It's be 55, 25.5. And then finally, the stress in the stainless steel, 277, 742, 0.25 pi times 4 inches squared. And when you calculate that, I got 22,102 pounds per inch square. So those are the stresses in the aluminum, the bronze, and the steel. So just like we've done previously, the way we found the force in the rod was to see how far it would expand past the wall if there was no wall, and then calculate the force required to push it back to the wall. And then, of course, to find stresses, you just take the force divided by the area of each part.